Okay. So this section 1.4 talks about this idea called continuity. Okay, and I mentioned it before. Okay, continuity. Okay, basically I like to think of continuity as being able to draw a function from beginning to end across the whole range of it, across its whole domain, and not ever have to pick up my pencil. Okay, so being able to, so many of the functions that we've been dealing with so far are continuous. Like our parabolas that open straight up, continuous, right? Because I can draw them all with one pencil stroke. Our cubics, so many of those. And we say continuous across its entire domain. Okay, there's basically 3 different types of discontinuity, and I talk about it here in the textbook. One is where the function's not defined. Okay, so this is the first type of what we call points of discontinuity, where the function is not defined at that point. So it'd be like an open dot, so it's not defined at C. Another point of discontinuity would be where the limit does not exist, like where the left and right bounded limits aren't the same thing, right? Because as we approach over here, this approaches this number up here, right? Mm-hmm. This one approaches this number down here, so they don't go to the same thing. So that limit does not exist, so that's the second type of discontinuity. And then the third discontinuity is where the limit does exist. Like here, the limit would be this number here, right? But the function value is actually down here. So the limit and the function value don't match. Okay, so that's the third type of discontinuity. Okay, so we have basically 3 different types of discontinuity. The function, so for a function to be continuous, it basically has to match all of these things. It has to be defined at that point. It has to have a limit at that point, and the limit has to equal the function value. Or really, for the most part, this third one is, can you find the limit by just directly substituting in? Okay, and that was a lot of our problems on the last section. We could just direct substitute in. If you can just direct substitute in to get the limit at that point, it's continuous at that point. Okay, does that make sense? So that's the idea of continuity. So a lot of these questions will say, discuss the continuity of this function. So here, example 1, that's what they have us do. And the easiest way to discuss the continuity is to just graph them. So if we're discussing this function and its continuity, okay, there's no way, so here's the function, 1 over x. There's no way I can draw that function without picking up my pencil, right? Because here at 0, right here at 0, if I take the limit, first of all, this function is defined everywhere except for at 0, right? So it's, first of all, it's not defined there. But then if we look at the limit, as I approach 0 from the left, I go to like negative infinity, right? If I approach it from the right, I go to positive infinity. So that limit does not exist. Hence, it's not continuous. It's continuous everywhere over here, right? I can draw that whole side. It's continuous everywhere here, but it's not continuous at 0. So a lot of times when we talk about a function's continuity, we talk about where it's not continuous or it has a point of discontinuity. Okay, does that make sense? So this one would say it has a discontinuity at 0 because the limit does not exist, right? That limit does not exist there, okay? Whereas another one that has a point of discontinuity, y equals, I don't want to do y. Let's do a divide. Numerator, we want x squared minus 1. And then x minus 1. Sometimes we have to not only use the graph, but use what we know about domain. Because if I just look at this graph here, it looks continuous, right? Because it looks like, sure, I can draw this whole thing, right? Except there's this crazy thing that happens over here at negative 1. No, positive 1. Forgot when I was doing positive 1. I get that undefined because of the denominator, x minus 1, it's undefined at 1. So this has a point of discontinuity at 1 because the function does not exist there. Okay, so again, when we're talking about continuity, we describe its points of discontinuity. Okay, and then does that kind of make sense? All right, so to help us in this discussion of discontinuity, we deal with one-sided limits, which we've already talked about one-sided limits before. let's go back to black. Okay. We talked about it when we talked about a limit not existing, meaning as we come in from the left and we come in from the right. So that would be like in this situation, because as I come in from the left here, I approach this number up here, right? As I come in from the right, I approach a different number. So there we say the limit does not exist. So it's helpful to be able to talk about that right-handed and left-handed limit. And that's where we get into those one-sided limits. So again, if you remember the limit as x approaches c with a little negative on top of f of x, that's coming, that little negative tells me we're coming from the left, right? Come from the left side. Okay. Whereas the limit as x approaches c with a little positive up there of the function, that comes from the right. Okay. So for a lot of these, you are basically just going to have to denote whether you come from the left or come from the right, and then look at the graph and approximate what number you're coming to. Okay. So for example, example 2, it asks us to find the limit as x approaches -2 with a plus sign on it of the square root of 4 minus x squared. It wants us to find that. Okay. So first of all, I could possibly direct substitute into there, like maybe try putting a -2 into there, but I'm going to look at the graph first. Square root of 4 minus x squared. Okay, isn't that pretty? Nice little half circle. So we want to approach -2 from the right. Because first of all, I can't approach it from the left, right? There's nothing on the left side of this. So I can only approach this from the right. And it looks like it's getting super, super small. And actually at that point it is 0. So I could direct substitute here, but that limit would be 0, right? But I can't come in from both sides, right? So really I can only talk about a one-sided limit at this point, since I can't come in from the other side as well. And that's the same as this one. I can only come into 2 from the left because there is no right of 2. Okay. So the one-sided limit of this would just be, what are we approaching? 0? Okay. Direct substitute in there. Okay. I just wanted us to get through 24. Yep. And the very last thing is we have to talk about the greatest integer. Let's go to the next page. Okay. We've seen them in pre-calc. The greatest integer function is the round. I always like to call it the round down function. Okay. And the symbol for it, if you remember, it looks like it's got like square brackets with the line on each side. And what that does is whatever you put in it, it rounds it down to the nearest whole number. Okay, so if we were to go ahead and plug in some x's and y's in here, let's go ahead and let's create a table. Like if I put in a 6, it's going to round it down to the nearest whole number, which is 6. Yep, so like 7 would be 7, but 6.5 would be, it's going to round it down 6. 6.75 is going to be 6. Basically anything in between 6 and 7 is going to round it down to 6 until I get to 7, and then I'll get 7. So then the graph of this is actually really funny. It's called a step function for a reason you'll see here in a minute. So let's go ahead, let's use blue. When I put in a 0, I get 0, right? When I put in a 1/2, I get 0, gonna round it down, right? When I put in a 1/3, 0, gonna round down. When I put in a 0.75, 0, it's gonna round down. Basically, if I put in anything in between there, it's gonna round it down to 0. Until I get to 1, there's an open dot here at 1, because when I get to 1, it's gonna give me out a 1, right? And it's gonna give me a 1 for any of these numbers in between here until I get to 2, right? And then at 2, it's gonna give me here, okay? Do you see how this So this function is gonna look like this, close dot, open dot, close dot, open dot, and then close dot, open dot. Hence why it's called a step function, because it looks like stairs, right? Okay. But this function really lends itself well to the discussion of one-sided limits. Because if I was to take the limit, let's say as I approach 3 from the left of this function, and take the limit as I approach 3 from the right. Okay, so if I approach 3 from the left, so 1, 2, 3, I'm approaching 3 from the left, I'm always gonna get 3, right? If I approach 3 from the right, I'm always getting 4. So the limit as I approach from the left is 3. As I approach from the right is 4. So the left side and the right-handed limits for any of our whole numbers are not the same. What is the continuity like of this function?
They're not the same.
Okay, is it continuous?
No.
No. Does it have points? Where are its points of discontinuity? A lot of them?
Yeah.
Right? Yeah, because the left and right-sided limits aren't the same at every whole number, right? So this has a point of discontinuity at every whole number. It has, or every integer, because it's true for the negatives too, right? So it has a point of discontinuity at 0, 1, 2, 3, 4, 5. It has an infinite number of points of discontinuity. Basically, at any of our integer values, it has a point of discontinuity. So not continuous because of this, right? The left and right-handed limits are not the same. Okay, you can graph this in your graphing calculator. Okay, it is the int function. You can find it, so it's int of x. You can find it in your, one way is in your catalog. Another way is, I believe, math. If you arrow over to probability. Oh no. Yeah, go down there a little bit. No, that's random integer. I'll keep going. Is there anything below that? No. Okay, so back over to number then. If you just hit the left arrow, then we'll be over. There it is, option 5. That's the greatest integer function. So you can graph it in your y equals